All right, for today's midterm review, we'll be looking at a few questions where we need to consider the effects of wind or not. And so it's kind of like a dynamics problem that's extending ideas from kinematics. You may recall that kinematics is a study of motion where we don't care what's causing that motion. Once things are moving, we can predict where they're going to be, when they're going to be there, how far away, and things like that, typically using equations of motion. But forces are things that cause changes in motion. Sometimes the forces that cause those changes in motion are important. This question, the only force that we really need to consider is the force due to gravity. The question reads, the acceleration of free fall on the moon is 1.6 meters per second squared. Just as sort of a chance to get some further review out of this, let's remind ourselves that that's really a value of g, right? The acceleration of free fall we call local g. It's local to the object that's creating that gravity field, in this case, the moon. But on Earth, we know that g has a value in acceleration of free fall of 9.81. And a way to think about that is because it is an acceleration, which is a change in velocity over time, that on Earth, things gain 9.81 meters per second of velocity every 1 second they fall, right? And so that's a helpful way to sort of remember what acceleration is and why it is a measure of the strength of the gravity field to say how much will things accelerate, under the influence of that. If you were to look at a graph of acceleration against time, then you would get choice D here, not speed against time. Like all these, answers were plotting speed against time. The acceleration against time for the moon would look like this. It's a constant 1.6, okay? Which is why we can kind of eliminate choice D. Like it can't start out with a non-zero speed because the word drops disqualifies that. Like if we're dropping something, then its initial velocity, its initial speed is 0, which agrees with choice B, choice A, and choice C, right? They all start with 0 velocity. So we can't figure out which one is correct based on that alone, but we can disqualify choice D by saying, well, it's got to have 0 initial speed, right? This is for a student who may confuse this with an acceleration time graph. This would be the correct plot if we were looking at acceleration as a function of time. It's constant 1.6 meters per second squared of acceleration. Or on Earth, this number would just be higher, right? It'd be a constant 9.81. Again, neglecting wind resistance. Question 7 that we're going to do in a moment here, we're back on Earth and we're dropping a tennis ball out of a tall building. Something to look forward to. But while we're still considering, this feather dropping on the moon, okay, the moon has no atmosphere. If the moon did have an atmosphere, then we might expect a velocity time graph or a speed time graph to be one that's going to resemble something we've seen before, where it's going to level off and reach a terminal velocity, kind of agreeing with choice C, right? Like we've done some physics of skydiving before, and we looked at velocity as a function of time, and we remember the graph kind of looks like that, right? It's accelerating initially because there's weight, but then as the drag force becomes more pronounced, it eventually equals the weight, and we reach this top constant velocity, this top speed. So this is kind of like if the moon did have an atmosphere, well, then eventually it's going to sort of level off its speed because there would be effects of wind. Because they say the moon has no atmosphere, we can discard choice C. Like this would only be if the moon did have effects of wind resistance. Choice B is like, it starts out 0, and then it's like the rate that it's sort of like picking up speed is increasing, right? So here it starts out like shallower and then it gets steeper, right? So the slope of this velocity time gives acceleration. And it's like it starts out with lower acceleration and then, sort of picks up. Or this one is just constant acceleration, right? Which is what we said we have, right? Like if we looked at a plot of acceleration against time, it would be constant. Here, there is a constant slope, right? Like the derivative of this is that, okay? And so that's why choice A is correct. Because there is no atmosphere, we would expect this thing to just have constant acceleration so that after 1 second of time, the thing is moving 1.6 meters per second in terms of its speed, okay? So there's no inflection, there's no sort of curve either this way or that way. This is kind of like what a displacement time graph would look like for something that's accelerating, right? Because the slope of displacement time graph gives velocity. It's picking up, sort of velocity until it reaches sort of that top speed. So this is more like, this would be a student that confused it with an acceleration time graph. This would be a student that confused accelerated motion, what a displacement time graph would look like. This would be like displacement, S for displacement, not for speed. And that would be corrected out. So the correct velocity time graph or speed time graph here, where the sort of vector nature of it doesn't matter too much, it's falling down on the moon, would just be choice A. Now on Earth, okay, a tennis ball is released from rest at the top of a tall building. Note the language is slightly different, like they could have said drop, that means released from rest. Here it's a little bit friendlier, reminding you like the initial velocity is 0, it's released from rest. Which graph best represents the variation with time t of the acceleration A of the ball as it falls, assuming that the effective air resistance is not negligible. So here they give us 2 clues that we need to consider wind resistance. One is the word tall. Like, why tell us it's a tall building? They're saying give air enough chance to act on this thing, okay? And if that wasn't clear enough, they explicitly state it right here, like the effects of air resistance are not negligible. You must consider them to get the correct answer. If the effects of air resistance were negligible, which sometimes they do give you permission to just say, hey, ignore wind, air resistance is negligible, then it would be choice D, right? Like we said, like just a constant acceleration. There's nothing taken away from that. And so we can kind of eliminate choice D as the incorrect answer because of this word not. We do need to consider what the wind is going to do. So it's not going to be a constant acceleration, okay? Which other graph best represents the variation with time t as it falls, assuming, air resistance is not negligible? So choice D can't be correct. Is there any other option up there that can be eliminated as obviously incorrect for some reason that you could point out? Yes. Say it again. Why is B incorrect? Yeah, it's like it starts out non-zero and it decreases acceleration to some non-zero value. It'd be like it starts out at 9.8, but then it kind of drops off to like 2, but it's still accelerating at 2 meters per second for some reason. Well, why would that not, sort of be the case? So I think you're right. Yeah, like B doesn't seem reasonable. Like it's going to sort of keep decreasing, but it's going to decrease to what? C can't be right because look, it's starting out with 0 acceleration. Okay, and it'd be like if something like kind of floated there or something, like you drop it, it's not accelerating, but then it picks up acceleration. This is more like what the velocity time graph looks like, right? When something reaches terminal velocity, like we talked about, right? It starts out with 0 velocity, but the slope there is the acceleration, which is non-zero, and then the slope goes to 0. It's like we want to consider a graph like this as the correct velocity time graph for this situation, right? This tennis ball will reach terminal velocity. If we consider what forces give rise to this velocity time graph, you may recall the parachutist problem where we said, you jump out of an airplane, you got weight that's going to make you accelerate, the acceleration due to gravity. But then you pick up so much speed so quickly that you crash into enough air that the air resistance starts to sort of subtract away from your, weight going down. And so your net force sort of decreases and you start to level off until eventually you're crashing into so much air that as far down as your weight is acting, the drag force is acting up with equal force. At that point, the sum of the forces is 0. And if we bring some form to our thoughts with Newton's second law, or the special case of Newton's second law where the mass is constant, then we know that as we sort of approach this terminal velocity, the acceleration is 0. If we're going at a constant speed, the slope of this part of the graph is 0, and the slope of a velocity time graph gives acceleration. And so I say, oh, that's the part where the acceleration has gone to 0, right? Like you give wind enough time to act on something, you let something speed up and accelerate, eventually it crashes into so much air particles that they equal the weight that made the thing accelerate to begin with. And now it's no longer accelerating. It's just traveling at top speed, terminal velocity. And so indeed, we're looking for the graph that starts out non-zero. And so we disqualify sort of this answer. but it's going to approach zero, right? Not some non-zero value. Like it'd be like it's going to keep accelerating. It'd be like if the velocity time graph kind of went like this and ever climbed, you know, like a constant rate, but it kept accelerating, kept on picking up speed, you know, for some reason. Like, no, eventually it's going to pick up enough speed that the weight, you know, and the drag force are equal, and the acceleration goes to zero. What agrees with choice A? That's why A is the best answer for that one. So here we do have to consider wind. Now, with the first one, we were kind of considering wind also, but just like the absence of it. I had to say, hey, no atmosphere on the moon, so it's going to look a bit different, right? The physics is a bit different. I'm going to go ahead and stop the video here, but we'll see you next time for a calculation involving some change in momentum.